Welcome to the deep dive.
Great to be here.
Today we're tackling a really foundational story. It's about how our whole understanding of the physical world shifted, from Aristotle right through to Newton.
Yeah, it's a huge leap. Our main source here is excerpts from History of Classical Physics, from Aristotle to Newton.
And the goal for you, listening, is to really get a feel for that journey, how we went from seeing the world through, well, almost philosophical lenses.
They're seeing it through mathematics, right? Understanding the forces, the motion. It's about those big shifts in how we even perceive nature.
Exactly. And those fundamental questions they started with, they're still kind of driving us, aren't they?
Absolutely. What's the world made of? Why does stuff change? Basic questions, but, well, they lead everywhere.
And you see this incredible evolution from just thinking about it philosophically to actually describing it with math.
Yeah, those two questions, what is it and how does it work? That's the core, really.
Yeah.
It's amazing how those simple curiosities launched everything.
What really grabs me is that massive jump from Aristotle's physics, where Earth stuff and heaven stuff followed totally different rules,
Right, like two separate universes almost.
to Newton, where suddenly, boom, one set of mathematical laws covers everything. Apples falling, planets orbiting, it's all the same physics.
That's a great way to put it. Aristotle had this sharp divide. Up there, perfect, unchanging heavens made of ether, moving in perfect circles. Down here, well, messy Earth. Four elements, things changing, moving in straight lines, mostly down.
And that division, that created problems, didn't it? When observations didn't quite fit those neat boxes.
Huge problems.
Yeah.
And those problems, those inconsistencies, are really what fueled the whole transition we're talking about.
So we're going to focus on two main sticking points for Aristotle's physics, the things that really paved the way for Newton.
Right. First, the way planets seem to move up in the sky. Kind of erratic.
And second, something much more down to earth but just as tricky, how projectiles, like an arrow or a thrown stone, actually keep moving after they leave your hand.
Okay, let's dig in. Where did the cracks first start appearing in that Aristotelian worldview?
It's amazing, isn't it? Just looking up or watching something fly could unravel centuries of thinking. Let's start with the heavens. Aristotle and Plato before him, they figured the heavens had to be perfect.
And perfect meant perfect shapes, perfect motion. So, uniform circular motion, everything moving smoothly in circles at a constant speed.
Sounds elegant, nice and tidy. But the planets, they didn't quite cooperate, did they?
No, they really didn't. The big headache was retrograde motion.
Ah, the backward loop.
Exactly. You watch Mars, say, night after night against the background stars, and it mostly moves in one direction, but then it seems to stop, go backward for a bit, and then forward again.
Which is hard to explain if it's just moving in one big, steady circle around the Earth. The name planet even comes from the Greek for wanderer, right? Because they seem to wander against the fixed stars.
Precisely. And another problem was brightness. Planets like Venus change brightness quite dramatically. If they were always the same distance, moving in perfect circles, why would their brightness change so much?
Good point. So perfect circles weren't quite cutting it. How did they try to, salvage the idea?
Well, the most famous attempt, and incredibly influential for centuries, was Ptolemy's system, back in the 2nd century AD. He stuck with the geocentric idea, Earth at the center.
Okay.
And to keep the perfect circle idea alive, he came up with this ingenious system of deferents and epicycles.
Right, epicycles. Can you break that down?
Sure. Imagine the planet isn't riding directly on the main circle around the Earth. That main circle is the deference. Instead, the planet is moving on a smaller circle, the epicycle.
Okay.
And the center of that little epicycle is what moves along the big deferent circle.
Okay. Like a little circle riding on a big circle. Kind of like the spirograph toys.
Kind of, yeah. It allows for more complex paths, loops, and things. But it got even more complicated. To make the predictions really match what astronomers were actually seeing.
To save the appearances, as they said.
Exactly. Ptolemy introduced something called the equant. This was a point near the center of the deferent, but not quite at the center. And the trick was, the center of the epicycle appeared to move at a constant angular speed only when viewed from this offset equant point, not from the Earth's center or the deferent center.
Whoa, okay, that sounds like bending the rules of uniform circular motion quite a bit.
It absolutely was. Mathematically, it worked surprisingly well for predicting where planets would be. His book, The Almagest, became the standard astronomical textbook for over 1,000 years.
So it gave good predictions, but the underlying model was getting really complex and maybe a bit artificial.
You could say that. It needed constant tweaking, adding more little epicycles, adjusting speeds as observations got better. And it didn't offer a clear physical reason for why things were set up this way. Like, why did the epicycles of Mars, Jupiter, and Saturn seem strangely tied to the position of the Sun in the model? It lacked a convincing physical story.
It feels like they were really determined to hang on to that Earth-centered perfect circles idea, even if it meant building this incredibly elaborate mathematical machine.
They were. It shows how powerful those philosophical commitments were. But okay, while Ptolemy's system dominated, it wasn't the only game in town, especially when we look at contributions from Islamic civilization.
Right. Our notes highlight their importance. What was their role?
Oh, absolutely crucial. Starting around the 8th century during the Islamic Golden Age, scholars did immense work preserving and translating Greek texts, including Ptolemy's Almagest. Without them, much of that knowledge might have been lost to Europe.
So preservation was key. But did they just translate or did they add to it?
They definitely added to it. They weren't just scribes. They developed much better astronomical instruments, things like the astrolabe, the quadrant allowing for far more precise observations than before.
Better data always helps.
Always. And better data often leads to better math and new questions. Mathematicians like Nasir al-Din al-Tusi came up with clever geometrical tools, like the Tusi couple, which could actually reproduce some linear motion from circular motions, potentially simplifying parts of Ptolemy's system.
Interesting. So they were refining the models.
Refining and also critiquing. Thinkers like Ibn al-Haytham, also known as Alhazen, raised serious philosophical objections to Ptolemy's model, especially the equant. He felt it violated the principle of uniform circular motion too severely. It just didn't seem physically real.
Questioning the foundations.
Exactly. And others like Al-Biruni really stressed the importance of empirical observation, actually checking if the models matched reality. They weren't just accepting Ptolemy unquestioningly.
And wasn't there an early idea related to inertia?
Yes. Ibn Sina, or Avicenna, developed a concept he called male, which translates roughly as inclination. It was an idea that a mover imparts something to the object, an internal tendency to keep moving. This later developed into the theory of impetus.
So not air pushing it, but something in the object.
Right, a precursor to inertia. And crucially, some scholars, like Ibn al-Shatir in the 14th century, even developed alternative geocentric models that were mathematically equivalent, in some respects, to Copernicus's later heliocentric model, just viewed from Earth's perspective.
Wow, so the groundwork for alternatives was being laid much earlier.
Definitely. And when this vast body of Islamic scholarship, with its observations, mathematical tools, and critiques, eventually made its way to Europe during the Middle Ages and Renaissance, it provided fertile ground for the next big leap.
Which brings us right to Copernicus, the big shift. Heliocentric. Sun-centered?
The Copernican revolution, yeah. So the Renaissance is in full swing. There's this rediscovery of ancient Greek texts, including Aristarchus, who had actually proposed a heliocentric idea way back.
So the idea wasn't totally new, just dormant.
Pretty much. Combine that rediscovery with a growing feeling that Ptolemy's system was just too complicated, too messy, maybe not even accurate enough anymore.
All those epicycles getting out of hand.
Right. And add in a philosophical current, Neoplatonism, which kind of revered the sun, saw it as this divine central source of light and reason. Putting the sun in the center suddenly felt fitting, almost noble to some.
So a mix of practical problems, old ideas resurfacing, and a philosophical shift.
Exactly. And Copernicus, who knew about earlier astronomy, including the Islamic contributions, put it all together in his book, De Revolutionibus Orbium Coelestium, published right around his death in 1543.
And his big argument was?
Simplicity and elegance, mainly. By putting the sun at the center and having Earth orbit it like the other planets, retrograde motion just happens naturally. It's an optical effect caused by Earth overtaking or being overtaken by other planets in their orbits.
So no need for epicycles just to explain that backward loop.
Not for the main retrograde motion, no. The whole system became mathematically neater, more harmonious in his view. He still used some smaller circles, mind you, because he stuck with circular orbits, not ellipses yet.
Okay, so not perfectly simple yet, but a lot cleaner.
Much cleaner. And you had that Renaissance spirit of questioning authority, challenging the centuries-old Aristotelian Ptolemaic view. It created an opening for such a radical idea.
Even though Copernicus might have presented it carefully, maybe just as a mathematical hypothesis?
Right, the preface added by Osiander framed it that way, perhaps to soften the blow.
The implications were huge, weren't they?
Enormous. Suddenly, Earth wasn't special, it was just another planet. The heavens and earth weren't separate realms anymore. Maybe the same laws applied everywhere. It opened the door for mathematics to describe earthly things more deeply. And it raised massive questions about motion. If the earth is moving, why don't we feel it? It implied this idea of relativity.
A total paradigm shift brewing, but it didn't happen overnight. People needed more proof, right? Which leads us to Tycho Brahe.
Tycho, the master observer, late 16th century. This guy was incredible. He built this amazing observatory, Uraniborg.
On an island, wasn't it?
Yeah, basically his own private science island, funded by the King of Denmark. And from there, without telescopes, remember, he made the most accurate measurements of star and planet positions that had ever been done. Just meticulous naked eye observation with sophisticated instruments.
That's incredible. Accuracy must have been paramount.
It was his obsession. And his data was gold. It was this data that revealed serious problems with the old Aristotelian picture.
How so?
Well, in 1572, a new star, a supernova, appeared. That shattered the idea of the unchanging, perfect heavens. Stars weren't supposed to just pop into existence.
Right, that's a big challenge to immutability.
Then, in 1577, he carefully observed a comet. His measurements showed it had to be moving beyond the moon, and its path seemed to cut right through the supposed crystalline spheres that held the planets.
So no solid spheres. Another pillar of the old model crumbles.
Exactly. His observations were directly contradicting core Aristotelian ideas. But interestingly, Tycho himself didn't become a full Copernican.
Really? Why not?
He couldn't quite accept a moving Earth. Maybe philosophical reasons, maybe perceived lack of direct evidence like stellar parallax. So he proposed his own compromise model.
The geoheliocentric one.
Yeah, the Tychonic system.
Yeah.
In his model, the Earth stayed fixed at the center. The sun orbited the Earth, but all the other planets orbited the sun.
Huh. That's a unique blend, trying to keep the best of both worlds.
Kind of. It incorporated the Copernican advantages for explaining planetary motions relative to the sun while keeping the Earth stationary. It actually fit his observational data quite well.
But he didn't explain why things move that way, the forces involved?
No, Tycho wasn't really a theorist in that sense. He was the data guy. His immense contribution was this incredibly precise data set. And that data set became the key that unlocked the next major breakthrough thanks to his assistant, Johannes Kepler.
Kepler. Okay, so he inherits Tycho's data. What does he do with it?
Kepler was a brilliant mathematician and a convinced Copernican. He believed the universe had an underlying mathematical harmony. He gets hold of Tycho's treasure trove of Mars observations, the best data available.
And Mars was particularly tricky, right?
It was. Its orbit is quite elliptical. Kepler spent years trying to fit Tycho's precise Mars data to various combinations of circular orbits following Copernicus. But it just wouldn't fit perfectly. There were always small errors, especially with Tycho's accurate data.
Those small errors matter in science.
Yeah, they absolutely do.
Oh.
And Kepler's genius was realizing the problem wasn't the data, it was the assumption of circles. After immense struggle, he finally tried fitting the data to an ellipse.
And it worked.
It worked beautifully.
Yeah.
That led to his first law. Planets move in elliptical orbits, with the sun not at the center, but at one of the two foci of the ellipse.
Wow. Goodbye, perfect circles, after thousands of years. That's huge.
Monumental. Then came his second law, the law of equal areas. He realized planets don't move at a constant speed. They speed up when they're closer to the sun in their elliptical orbit and slow down when they're farther away.
So variable speed, too, breaking all the old rules.
Completely. The second law gives the mathematical rule for that speed change. The line connecting the planet to the sun sweeps out equal areas in equal times.
Okay, so law 1 is the shape, ellipses. Law 2 is the speed, variable but predictable. What's the third?
The third law, the harmonic law, is maybe the most profound. It relates the orbits of different planets to each other. It states that the square of a planet's orbital period, the time it takes to go around once, is directly proportional to the cube of the semi-major axis of its orbit, basically its average distance from the sun. T squared equals r cubed, essentially, with a constant factor.
So it connects all the planets in the solar system with one mathematical relationship.
Yes. It showed there was this underlying mathematical architecture to the whole solar system. It wasn't just a collection of individual orbits. They were related in a precise way. This strongly hinted at some common underlying physical cause governing them all.
Kepler's laws sound like they move things from just describing motion to finding the precise mathematical rules of that motion.
Exactly. He wasn't just saving the appearances anymore. He was uncovering the actual mathematical laws based on rigorous analysis of the best empirical data. He paved the way for asking why the planets obeyed these laws. The stage was set for dynamics.
But even with Kepler's laws, people still had trouble accepting a moving Earth, right? Like, why don't we fly off? Why doesn't the wind constantly howl? That's where Galileo comes in again.
Right, Galileo was crucial for tackling those very intuitive, common-sense objections. His big contribution here was the principle of relativity.
The ship analogy.
The famous ship analogy, yes.
Yeah.
He argued that if you're inside a closed cabin on a ship moving smoothly at a constant speed, you can't tell it's moving just by doing experiments inside, dropping things, watching flies buzz around. Everything behaves normally.
Because everything inside the cabin shares the ship's motion.
Exactly. And the same applies to Earth. We, the air, the clouds, things thrown up, we all share the Earth's motion through space. So, relative to the Earth, a stone dropped falls straight down. We don't perceive the Earth's velocity because we're moving with it. Uniform motion is undetectable from within the moving system.
That's a really powerful counterargument to those intuitive objections.
It really is. And then, of course, Galileo turned his newly improved telescope to the heavens, and the evidence just piled up.
What did he see that was so revolutionary?
Oh, lots. He saw mountains and craters on the moon, showing it wasn't a perfect, smooth celestial sphere. It looked, well, kind of like Earth.
Blurring that heaven-Earth distinction again.
Absolutely. He saw 4 moons orbiting Jupiter. This was huge. It proved that not everything orbited the Earth. Here was a mini solar system, clear evidence against a strictly geocentric view.
A direct challenge.
Then he observed the phases of Venus. Just like our moon, Venus went through a full set of phases. This could only happen if Venus orbited the sun, not the Earth. It was strong evidence for the heliocentric arrangement.
Wow. So the telescope became a key witness for Copernicus.
Definitely. And he saw that the Milky Way wasn't just a hazy cloud. It was made of countless individual stars, far more distant than people imagined. The universe was suddenly much, much bigger and more complex.
So Galileo's work, both with motion principles and telescopic observation, really hammered home the flaws in the old system and built a strong case for the new one.
It did. He championed observation, experiment, and mathematical description, and he provided compelling evidence against the Aristotelian cosmos. Okay, so we've tackled the heavens. Let's shift back down to Earth and that other big problem for Aristotle. Projectiles.
Right. Aristotle said motion needs a continuous force, contact with a mover. So you throw a spear, what keeps it going after it leaves your hand?
His answer was, well, a bit strange. He called it antiperistasis. The idea was that as the spear flew forward, it pushed the air out of the way, and that air then rushed around the back of the spear to fill the void.
And pushed it along.
Yeah, supposedly the air rushing in behind it provided the continuous push needed to keep it moving.
That feels counterintuitive. Air usually provides resistance, drag.
Exactly. That was a major criticism even in ancient times. How could air, which normally resists motion, suddenly become the thing propelling it? And how could it provide the force needed to keep something heavy moving? Plus, the actual path of a projectile, that arc,
A parabola.
didn't really seem to fit with this idea of air just constantly pushing from behind. It wasn't a very convincing explanation.
So people looked for alternatives. We mentioned Ibn Sina, Avicenna earlier with his mail. How did that idea develop?
Right, Ibn Sina's concept of an imparted inclination was a key step. He suggested the thrower transfers a quality to the object itself, an internal tendency to continue moving. This quality would gradually fade due to resistance.
So the motive force is internal, not external air pushing.
Exactly. This idea, later developed in Europe as the theory of impetus, was a really significant departure. It located the cause of continued motion within the projectile, not in the surrounding medium.
And it acknowledged resistance, that the motion would eventually stop.
Yes. It was a much more plausible explanation for why things keep moving after being thrown and why they eventually slow down. And as we noted, Ibn Sina even suggested this might apply to the heavens too, hinting at a unified principle.
This seems like a crucial stepping stone towards inertia. Now, the Renaissance seems to have really picked up on these ideas about motion.
It did. The whole intellectual climate was changing. You had the rediscovery of other Greek thinkers like Archimedes, who was very mathematical about mechanics. There was a rise in humanism, emphasizing human reason and observation over just accepting ancient authority or dogma.
So more critical thinking, more looking at the world directly.
Definitely. Think of Galileo again, with his experiments on inclined planes. That's the empirical approach in action. There was also a strong Platonic influence, emphasizing the mathematical nature of reality, which you see clearly in Kepler and Galileo.
And technology was playing a role too.
Yeah, the development of things like better clocks, more precise instruments, even perspective in painting it all contributed to viewing the world as a kind of intricate, understandable mechanism. The universe is giant clockwork, almost.
So the Renaissance wasn't just looking back, it was actively testing, observing, and using math in new ways.
Precisely. It created the environment where these new ideas about motion could flourish. And that brings us to Jean Buridan in the 14th century, who really refined that impetus idea.
How did he develop it beyond Ibn Sina?
Buridan took Ibn Sina's qualitative idea and made it more, well, quantitative. He called it impetus force, and proposed that the amount of impetus an object received depended on two things: its velocity and its quantity of matter.
Quantity of matter sounds like mass.
Very much like a precursor to mass, yes. So impetus was related to both speed and how much stuff was in the object. This is remarkably close to our modern concept of momentum mass times velocity.
That's a huge leap. He's starting to quantify this internal force.
He really is. And even more strikingly, Buridan suggested that this impetus it would last forever unless acted upon by external resistance, like air drag, or an opposing force, like gravity.
Conservation of impetus. That sounds incredibly close to Newton's first law, the law of inertia.
It's practically knocking on the door. The idea that an object will maintain its state of motion, impetus, unless a net force acts on it. He shifted the focus from needing a continuous cause for motion to needing a cause for a change in motion.
Did he apply this to the heavens, too?
Yes. Like Ibn Sina, he suggested maybe God imparted impetus to the planets at creation. And since there's no resistance in the heavens, they just keep moving indefinitely. A single explanation for both earthly and celestial motion.
Buridan seems like a really pivotal, if maybe less famous figure in this transition.
Absolutely. His work was a major bridge between the Aristotelian view and the beginnings of classical mechanics. And you can definitely see the echoes of his impetus theory in Galileo's later work on inertia and motion.
Okay, back to Galileo then. Our outline calls his work a fundamental revision of understanding motion. What made it so fundamental?
Galileo really cemented the shift towards modern physics. His emphasis was relentless. Observe carefully, experiment where possible, and describe nature using the language of mathematics. He wasn't afraid to use thought experiments either.
Idealized experiments.
Yeah, like imagining situations without friction or air resistance to get at the underlying principles. His work with inclined planes is the classic example.
Tell us more about those experiments. How did they lead to inertia?
By rolling balls down ramps of varying steepness, he could slow down the effect of gravity and measure it carefully. He noticed a ball rolling down one ramp would roll up another connected ramp to almost the same initial height, no matter how gentle the slope of the second ramp was.
Okay.
So he reasoned, what if the second ramp was perfectly horizontal? If there was no friction or resistance, the ball, once rolling, would just keep rolling forever at a constant speed.
Because it would never reach its starting height, so it wouldn't know when to stop.
Kinda, yeah. It established that uniform motion in a straight line is just as natural a state for an object as being at rest. It doesn't require a continuous force to maintain it. That is the core of the law of inertia, a massive break from Aristotle.
So rest isn't special. Constant velocity is also a natural state.
Exactly. And he didn't stop there. He gave us the mathematical law for free fall distance equals 1/2 d times t squared, we're still 52, showing constant acceleration. And he figured out projectile motion.
The parabola again?
Yes. He showed it's a combination of two independent motions. Steady, uniform motion horizontally due to inertia, once launched, and uniformly accelerated motion vertically due to gravity. Put them together, you get a parabola. He described it mathematically.
So he's providing the mathematical formulas for how things move based on this new understanding of inertia and acceleration.
Precisely. He might not have had Newton's concept of force fully fleshed out, but he laid the quantitative groundwork and established that crucial concept of inertia. And we already talked about how his relativity principle and telescope observations defended the Earth's motion.
Right, the relativity argument explaining why we don't feel the Earth moving.
And the telescope showing the heavens weren't perfect and Earth wasn't the center of everything. It all tied together, undermining the old view and supporting a new, unified physics.
It really feels like the pieces are falling into place. Now, René Descartes comes into the picture. Where does he fit in? He seems more like a philosopher, but also a mathematician.
Descartes was hugely influential in the 17th century.
Yeah.
He had this grand vision to build a complete system of knowledge, including physics, based on clear, logical deduction, almost like geometry. His starting point was, I think, therefore I am. But he extended that rationalist approach to the natural. He believed motion was the fundamental type of change in the universe. Everything else was just matter moving around.
It's a very mechanical view.
Extremely mechanical. He famously envisioned the universe as a plenum, completely filled with tiny particles of matter, no empty space, no vacuum allowed. Planets and stars were carried around in giant swirling vortices of his matter.
Like cosmic whirlpools.
Exactly. It was a very visual, mechanical explanation, though it didn't ultimately hold up. But he also formulated some key principles for mechanics. He had a law of conservation of motion.
Similar to Buridan's impetus.
Similar, but different. Descartes defined it as quantity of matter times speed, not velocity, so ignoring direction. He argued the total amount of motion in the universe was constant, just transferred between colliding bodies according to certain rules he laid out. He also stated a version of the inertia principle. A body continues in its state, rest or motion, unless it collides with another.
And he also talked about relativity.
Yes, he recognized that motion is relative, that there's no absolute fixed point in space to measure it against.
Yeah.
But maybe his most lasting contribution to physics was inventing analytical geometry.
Connecting algebra and geometry.
Precisely. Using coordinates, x, y, z, to describe shapes and motion mathematically. This gave science an incredibly powerful new tool set. It became the language for describing physical relationships precisely.
So Descartes provided a philosophical push towards a mechanical universe and, crucially, the mathematical language to describe it.
That's a good summary. His specific vortex theory didn't last, but his emphasis on mathematical description, the mechanical philosophy, and concepts like conservation of motion and inertia were hugely influential on thinkers like Huygens, Leibniz, and ultimately Newton.
Okay, and that leads us to Christian Huygens. Our notes call him a bridge between Galileo and Newton. What were his key contributions?
Huygens was a Dutch physicist, mathematician, and astronomer, a real giant of the era. A lot of his work was incredibly important, but sometimes gets overshadowed because Newton published more comprehensively later.
What did he achieve?
Well, for one thing, precise timekeeping. He invented the first accurate pendulum clock based on his mathematical analysis of pendulum motion. He figured out the relationship between the pendulum's length and its period.
Why was accurate timekeeping so important for physics then?
If you want to study motion velocity, acceleration, you need to measure time accurately. Galileo had used his pulse or water clocks, which weren't very precise. Huygens' clocks were a massive leap forward, essential for quantitative dynamics. He also developed the balance spring for watches.
Okay, better tools. What about theoretical insights?
He made major contributions to understanding collisions. He formulated laws for elastic collisions, correctly using concepts related to conservation of momentum and kinetic energy, though he called it vis viva. And importantly, he understood momentum as a vector, having direction-correcting Descartes' scalar quantity of motion.
Yeah, that direction matters in collisions.
Absolutely. He also derived the formula for centrifugal force, the force needed to keep something moving in a circle, or the apparent outward force it experiences. Fc equals mv or r. He even coined the term centrifugal.
So he's quantifying the forces involved in circular motion.
Exactly. And maybe most significantly, Huygens really emphasized that force should be understood in terms of the acceleration it produces. He was thinking along the lines of F equals ma, even if he didn't state Newton's second law in its final form. He also refined the principle of inertia, understanding its application in non-accelerating inertial reference frames.
It sounds like Huygens had many of the key ingredients for Newton's laws.
He really did. His work on collisions, circular motion, pendulums, and his focus on force causing acceleration provided a lot of the crucial groundwork. He filled that gap between Galileo's initial descriptions and Newton's grand synthesis.
So we've got Galileo describing motion, Kepler describing planetary orbits, Descartes providing a framework and math tools, Huygens refining concepts like force and momentum. But there was still something missing, the missing link between kinematics and dynamics.
Yes, exactly. By the mid-17th century, they were getting really good at describing how things moved. Kinematics, Galileo's laws of falling bodies, Kepler's laws of planetary motion, these were incredibly accurate descriptions.
But not the why.
Not the fundamental why. Not in a unified way, dynamics. Galileo didn't explain the origin of gravitational acceleration. Kepler knew the planets followed ellipses, but he didn't know what force held them in those orbits, though he speculated about magnetic forces from the sun. Descartes' conservation of motion was important, but his rules for collisions weren't quite right, and his definition of force wasn't precise. Huygens had quantified centrifugal force, but hadn't yet tied it all together into a universal law of gravitation or motion.
So Lots of pieces, but no single picture that explained both apples falling and planets orbiting using the same fundamental laws.
Precisely. They lacked universal dynamical laws. Mathematics was the language, yes, but it hadn't yet revealed the underlying cause. What force makes things fall? What force bends the planet's paths from straight lines into ellipses? How do terrestrial mechanics and celestial mechanics connect at the deepest level?
Although you mentioned conic sections, parabolas, and ellipses hinting at a mathematical connection.
Yes, mathematically there were hints of unity. But the physical agent, the universal cause of these motions, was still missing. That was the challenge. What general law or force governs all motion everywhere?
And answering that required, well, a revolution.
It required a causal, quantitative, and universal framework. It required Isaac Newton. His work, building directly on all these thinkers we've discussed, finally provided that synthesis with his laws of motion and universal gravitation. But that's perhaps a story for another deep dive.
Indeed. What an incredible journey, though, tracing these ideas. We went from Aristotle's philosophical divided cosmos
Through all those challenges, planets wandering, projectiles flying,
to the breakthroughs of Copernicus, Brahe's amazing data, Kepler's laws, Galileo's observations and insights into motion and relativity.
and the crucial groundwork laid by thinkers like Ibn Sina, Buridan, Descartes, and Huygens, developing concepts like impetus, inertia, and the mathematical tools needed.
It really highlights how science builds, doesn't it? Each step resting on the ones before. This whole period just set the stage perfectly for Newton's grand synthesis.
It absolutely did. It was the essential foundation for classical mechanics, and really, for modern science as we know it, a truly transformative period in human thought.
And just to leave you with something to think about, consider how central questioning established ideas was to this whole story. The willingness to look closer, to trust observation, to invent new ways of thinking, even when it went against centuries of tradition.
Yeah, it makes you wonder, doesn't it? What deeply ingrained assumptions do we hold today about the universe, about reality, that might seem just as strange or incomplete to future generations as Aristotle's physics seems to us now? What fundamental shifts might still be waiting around the corner?
A provocative thought indeed. Thanks for guiding us through that fascinating history.
My pleasure. It's an amazing story.